Right, what up, you two? Wearing the good old NASA t-shirt. Alright, I did promise Jay a shout out as well, so this one's for you. And to James as well, Lee, and a whole bunch of other people as well. Alright, and I'm sort of going a little bit Elon Musk here. It's got to be said. Alright, okay, look. I'm just going to give you the presentation then, and we'll have a little look at the design brief, and then we'll see what we've got in the background. All right. So this one stems from this whole article here. All the links are given below. Now, NASA wants to put a nuclear power plant on the moon by 2030, and apparently I can help. Well, this article dropped about 3 days ago, but it appeared in my news feed a few hours ago. And I got to admit, I was sort of intrigued by this. So I dedicated 3 hours of my time to think about it. Right, let's have a look at the article, and I'll go Elon Musk sort of way with my ideas. We'll chuck it out there and see what happens. Alright. So the reactor will help sustain future missions on the moon, Mars and beyond, according to NASA. Oh, and by the way, I did check this out, and it literally does check out. There are 2 websites that go into this, and even NASA are serious about it. Okay, right, well, again, we'll sort of cover that. Right, so they have sort of illustration there. All right. So they open with, do you or a friend know how to build a uranium-powered nuclear reactor that can fit inside a 12-foot long by 18-foot wide, so 4 by 6 meters rocket? Can you get the job done by the end of the decade? If so, then NASA and the US Department of Energy would like to hear from you. We'll come to that in a minute. According to a statement from the Department of Energy's Idaho National Laboratory, or INL, on November 19, the lab is teaming up with NASA to put a durable, high-power, sun-independent fission reactor onto the moon within the next 10 years. The 2 agencies are currently seeking proposals from outside partners to get this lofty project started, with a submission deadline of February 19 of 2022. So I'm well within that time. Well within. Right. This hypothetical reactor would help turn the moon into an extraterrestrial base for human space exploration, including future manned missions to Mars, agency officials said. Quote, plentiful energy will be key to future space exploration, said Jane Reuter, the Associate Administrator for NASA Space Technology Mission Directorate in Washington, D.C., said in a statement, I expect fission surface power systems to greatly benefit our plans for power architectures for the Moon and Mars, and even drive innovation for uses here on Earth. That's interesting. The calls for proposals come with some basic guidelines. This is the point. The proposed reactor must be a uranium-powered fission reactor. That is, an apparatus that can split heavy atomic nuclei into lighter nuclei, releasing energy as a byproduct. in brackets by the way, nuclear fusion on the other hand involves combining two or more lighter atoms into a heavier one, also releasing energy in the process. We'll look at that in a minute. I've got some stuff about that, but whatever. Interestingly, the reactor must weigh no more than 13,200 pounds, which is 6,000 kilos, which is 6 metric tons. Interesting. And fit into a rocket with the dimensions listed above, which was, I do believe, 12 foot by 18 foot. We'll come back to that. Right. The reactor will be assembled on Earth, then launched to the Moon, where it must provide 40 kilowatts of continuous electric power for 10 years. Interesting. The reactor must also have temperature controls to keep the device cool. Awesome. The temperature on the Moon can reach more than 260 degrees Fahrenheit, or about 127 Celsius during the day. The request for proposals come while NASA begins ramping up its Artemis program, which aims to create a sustainable human presence on the Moon by the end of the decade. The program, which plans to return humans to the Moon for the first time since 1972, is estimated to cost around $93 billion. There's money to be had on this one, eh? Okay. Cool. There it is. Yeah, now I'm sort of going to go kind of Elon Musk here a little bit. But just before I do, there's a few things I want to look at, because I've done the maths on this. Well, they said on there, if you look here, right, it has to fit inside 12 foot long by 18 foot wide, which is 4 meters by 6 meters, right? Well, not quite. They're out by a little bit. I've done some of the calculations. We'll go through it. 12 foot long, right, 4 meters, which is 4,000 millimeters. We don't work with feet. It's not really done in engineering. Right? We tend to go by millimeters. It's more accurate. 18 foot width, they're proclaiming is 6 meters, or 6,000 mil. I think they're out by a little bit. The fact is, 12 feet is 3.6576 meters, or 3,657.6 millimeters. Right? That's long. So they're out by around 343 mil. And that's a lot. It is, in engineering terms. That's massive. 18 feet is actually 5.4864 meters, or around 5,486.4 mil. So they were out by 514 mil. Right. Now the weight, they're bang on with that, actually. They said 13,200 pounds. Well, 6 tons is 6,000 kilos. There's 2.2 pounds to a kilo. So it's 6,000 times 2.2, which is indeed 13,200. I was able to work that out. I'll just double check that one. Right, so they said 13,200. Okay, so what we want, 6,000, because, well, that's 6 tons, times by 2.2, and I made it out as 13,200. and I'm right. So the maths checks out. Right. Now, the power requirements for this is really interesting. But because they want 40 kilowatts of energy. Right. Now, they didn't say whether or not per hour or whether it's continuous or which the sort of situation is, but again, I've done the thinking. All right. So assuming at the lower end of it, which is unlikely, then for 10 years, if they were going to divide it down by each year, they would want 4 kilowatt hour per year, which is low. It's very low. It's about 300 watts per hour, because the 4 kilowatts, you would divide it essentially by 12 and end up with, about 0.3 or 300 watts. But I failed to take into consideration 12 months in a year. I did it for 10, so it would actually be around 500 watts per hour, or about 5 light bulbs. It's about half a kilowatt per hour, and that's not really a lot. It certainly wouldn't require what they're saying is a fission reactor. So, I don't think they'd be doing that. Right. So I'm assuming this is continuous power they want. So that 40 kilowatts an hour, right, for the whole 10-year duration contiguously, it's actually quite a lot. They're looking for 40 microwave ovens every day to be run. Every day for 10 years. Right. That looks like 40 of these, essentially. 40 every day for 10 years. That's a lot. That's actually quite a lot. And that thing weighs a lot. Well, we've sort of done the maths on this. So, your voltage, it basically works out to be voltage equals 1,000 times your power in kilowatts divided by your current. Or your power in kilowatts equals your voltage times your amps divided by 1,000. It's quite a lot. So 3,000 volt times by your 13 amps and then divide that by 1,000. Well, I'm quite close. I got to 39 kilowatt. So about a kilowatt out. That's not a huge amount. Right? So looking at this, 13 amps by your 40 kilowatt, it's about 520 amps, or so, is it? Something like that. Over the whole lot, something like that. I'm getting a bit confused, but it's 3,100 volt in total. If you break this up over 10 people, 300 volt over 1.3 amp, or we could do this at about 150 to 200 volt over sort of getting on for 2 amp. Right. Something thereabout, but it's doable, but it's quite a lot. It's a lot. Alright, let's just pause out. I'm going to have a quick drink and then we're going to talk about this whole difference between fusion and fission and sort of why NASA, they really want to go the fission route, not fusion. And for some reason they want this completely independent of solar power, which I'm intrigued by. My idea can be built for that, but I don't really see why you would. Why you would be independent of that when actually to incorporate it and run solar power in any event, given certainly how light these output caps are, you probably would. Right. Let's just pause that quickly and we'll come back. Alright, cool. So we're back. Alright, now just in case people don't really know exactly the difference between fusion and fission, I'm going to explain it in a nutshell. And it looks like I've been drawing cartoon faces. I might even get some of these put on a shirt, but you never know. Right, fusion essentially is taking two hydrogen nuclei and smashing them together. The idea being you get a huge bang and loads of energy released. Now, hydrogen being the lightest element in the periodic table, when you do this, which is what the sun does, you generate increasingly higher weight molecules. And the sun and all major stars does this. Well, the problem is, with super big stars, once they've done that, they generate helium. They try and fuse that because gravity tends to pull it all together, right? So they smash helium together and then they release heavier elements like oxygen, carbon, eventually all the way up to iron. You can't fuse iron. It won't. So basically what happens is smashes together, stays put, gets super hot, and everything on it starts to collapse, right? As does the outer shell of really big stars. When it hits essentially the core, it bounces out and it all blows apart, and you get supernova. Hydrogen bombs are also essentially the same thing. It's fusion, right? Really bad idea. To do this, again, you could either use hydrogen or uranium, and you're going for critical mass. Either slam it together or have enough of it in one area and you'll get critical mass and it will react. And you end up with the whole Hiroshima thing, which is not cool. And I suspect that's the reason why they want fission, not fusion. Fission, on the other hand, is a little bit different. Right? You're taking a one atom and then you're hitting it and breaking it apart. The idea being that's a heavy atom, so that would be something like uranium-235 or 238, whichever. You're breaking it apart, and then when you do, you're getting lighter elements out of it. This still requires an energy input. There are no free lunches here. You can't get energy from nothing in that way. If you want to split that atom, you still need energy in. Energy in, energy out. Whatever you put in there, you're not going to get 100% conversion out of it. Law of thermodynamics, essentially. You're not going to get 100%. Because you're going to lose an element to that to heat and light. That's the problem. But that's fission as opposed to fusion. At the bottom here, you see solid, liquid and gas. You look at the amount of compounds in the solid, right, or molecules in an area, there's more. That's why solid. Liquid, those molecules are not as tightly bound. So they're more free-flowing, and in gas, they're even looser bound. So somewhere between here and here is easier, because then we can hit each one and split them. We don't really want to be using a solid for that reason. It would take more energy to break them apart. Liquid less so, but gas even easier. Right. So I guess now we just pause out and then we come to my my presentation to show you what I've sort of come up with, only in about 3 hours. Bearing in mind I only got this in my sort of news feed today, so 1 minute. Alright, okay, so it's not bad for 3 hours of mind thought, even though it does look like I've tried to draw some sort of food blender. It does indeed look like that, but I'll be able to explain what the hell is going on. Alright. We just have a solid base here. This would be sort of on the lunar surface, if you would. This here would be a rotating base. Either that or this part here would be rotating. There's a couple of ideas to be worked out with this. Either we could have this part rotate counterclockwise, or rather this top part here that way and this part the other. Sort of like a kind of twisting motion, possibly, but or as one, like a glorified centrifuge. We'll come to that in a minute. Down here we have uranium or moon dust. I say moon dust because moon dust, believe it or not, is massively radioactive. Right? It largely is. Well, you look at it. There's no atmosphere or sort of no solar protection on the moon, is there really? Yeah, so it's heavily irradiated. So I'm sure if you took a Geiger counter to the moon, you would get some very interesting readings. All right. There's no ozone layer either, for that matter. So we could take our uranium, either from Earth or moon dust already there, enrich it and chuck it into a system. Right. Down at the bottom we have supercooled nitrogen gas, or sort of liquid nitrogen would be even better. It needs to keep the internals of this cool. They did say they want cooling on this. Yeah, well, cool. We'll do that. Now the thing is, also, you do get a light side on the moon as well. I do believe in the design brief they didn't want solar panels there, but we could always include one anyway. So any sunlight coming in would provide shade on that to stop it overheating. So we could even still use that for powering our inputs, which we'll come to in a moment. And then we have our waste out. So after our reaction, well, we need to get rid of our waste material, don't we? Which will be plopped out the bottom, or equally elsewhere, wherever we want. Now, there's a couple of ways we can go with this. Right. We either can have an electricity output off of one side, or from within our reaction chamber in the middle, from our sort of dirty diamond kind of cold fission reaction, not really so much cold, because certainly in the middle, alright, that's going to get really hot. That's kind of cool and useful, because here we would have a liquid circuit. Right? So like water or something like that. So water comes, right, goes in, right, or rather hot water comes out, so this would all be hot. Drives a turbine, and then we get an electrical output on there. That hot water goes through a condenser column and is cooled and essentially put back in as a closed loop. So there's a couple of potential ways we can go with that. Right. And at the top end, we would create most of the reaction from high-powered lasers. Now, the lasers are an interesting point because you can indeed get these things up to a really high temperature. Well, laser cutting and certainly plasma cutting is a thing. So, yeah, they can do that. And if they can cut metal, then uranium is essentially basically a metallic element, then they should be able to do that. Alright, so that would look like the sensible way to do it. The inside of this thing, I would say, would be like kind of an hourglass shape, almost, with your dirty diamond in the middle. Now, diamond is interesting because it would allow a laser in it. We can make diamonds by compressing carbon, but we would want that diamond to have metallic properties as well. Well, they did say hypothetical. If it was, then it could be held in place by magnets. That would allow us to start rotating the rest of this up to really high speeds, allowing that diamond to get really super hot. When it does, then we can chuck our sort of uranium moon dust or whatever we want into that, and then fire a pulse laser into it. Right. We wouldn't want the laser continuous because it will burn the laser diode out. So just to get rid of that and show you what it would sort of look like. It would be goes its frequency like that. Where that's on, that's off, something like that. And here, in between each pulse, would be a few milliseconds or so. So it'll be strobed, so you don't burn your laser diode out. If it was continuous, then you would need to cool your laser diode. And laser diodes typically made of ruby, if they're red or whatever, but they typically are like this. And then obviously you have gas in there, and you run a voltage up, and then you would have some kind of output, right? Sort of like that. So we'd want to strobe it. Really high power. Because what we're after is those gas particles there, or somewhere in between, and start splitting them. Like that. See? And when we do, huge amounts of energy is given off and lighter elements, which again on our wastegate on the output could also potentially be sort of reused. So this is going to make lighter elements, so you'd probably have some sort of carbon there, maybe oxygen or water, oxygen, hydrogen, possibly, well, whatever, right, depending on what we're essentially splitting. But key is the whole moon dust thing as well. And again, it doesn't violate any laws. Right. Power as well, I don't know if I covered this part, but you have a voltage in and a negative there as well. I've ruined that board, so I'm just going to pause this quickly and essentially show you what I mean 1 minute. Alright, so the concepts of sort of an electric motor. Basically, you have a sort of rotor there, and you would have a bunch of magnets on it. So, and then you would have sort of a stator, and then the rest of the frame. Right, well, that would be a north, and that would be a south. Right. And you generate loads and loads of magnetic fields in here, and then this thing begins to turn, because you're going to induce sort of something like that. Right. So that's it face on, and it would essentially kind of look like that from the side, and then that sort of rotates. Right. Well, that is what we want here to get that thing rotating. Now, we can take batteries with us. We can do. Batteries weigh too much, but we certainly have chargeable capacitor banks. We can do that, and that's probably the way to go. What we want is to kickstart this thing over like a starter motor. Right? So it's like a starter in a car. Right. Once you have that starter going, the rest of this, as long as it's fueled, would work. So it doesn't violate any laws of physics either. So there's nothing like sort of infinite perpetual motion, which is, it's BS, basically. So when we said it's about hypothetical engines, well, we want it realistic. Right? So again, with this, as long as we have some way of starting it, as long as we have some way of powering the initial laser sequence, as long as we have some way of putting fuel in there, then the rest of this can use to power itself. The example is really simple. I'll show you. 1 minute. That's the example. Right? No real difference. You get into your car, you turn your key, you have a starter motor down here which turns your engine. Right? Turns over the whole lot in your combustion engine. In the back, you have a fuel tank. That fuel is piped down into your engine. Right? This starts putting away, and then on the output you have your well, they're your exhaust. All your stored energy is essentially in there. That's essentially my idea in a nutshell, which actually now just looks like I've scribbled all over the damn board, and now you can't really make out much sense of anything. But you certainly see from the description. Right. Another example, let me show you. I've not drawn man sausage. That's a rocket. Right. And I would be sort of in there saying yippee. Alright. So the idea being is you would have sort of fuel in here and an oxidizer in here. Right. This is brought together and ignited, and it's kicked out the back. Right. But the fuel's already there. You provide the ignition, and then the reaction is self-sustaining. Similar to our strange sort of design. We have our uranium or whatever we want to put in. Right. We have an external power source to kickstart this thing. Starts the rotation off. Right. Either our liquid or nitrogen gas and our reactable material to help release the energy is pulled in. And our initial laser is fired off. The rest of it then switches over to our liquid circuit, right, and our turbine. And that's it, pretty much. Or we can go the direct output, which this thing still looks like a sort of weird food blender, really. Well, yeah, sort of. These parts are magnets across here, by the way, so it rotates. And as we said at the top here, we could have it so one side turns clockwise and the other side turns counter. Either way round it, I'll quickly show you what the internal chamber would look like, sort of in 3D. I'll try and draw it out 1 minute. 1 minute. Alright, so we'll give it a go at trying to draw it then. Right, so how would I think it would look? Well, we said we need some sort of diamond thing in the middle. But before we do, we need the outer casing. So it would look something like that. And we would need some sort of kind of diamond shaped thing in the middle, or maybe ball shaped. Ball, actually, yeah, ball would be better. So all this would sort of coalesce into one point there. That. So, and then you would have, obviously, well, you wouldn't see that, that's just the base. Your laser would, or several, would be sort of in there, and all of those beams will be angled into the middle. Then up here you would need 2 tubes. Well, you'd actually need 3. This one, and that. So this one would be for your U235 or 238. This one would be for your, what did we say, it would be our nitrogen. So nitrogen gas, or liquid. And this one out here would be for waste. This guy here is going to get really hot. So bear with me, we will need something to show that. Let's get rid of that. It's going to get really hot. Really hot. You see it? It's really burning up. So, what we would then have cold water. We'll just put that on a loop that goes behind. So that's a cold water there. But water is going to be hot here, isn't it? So it'd be like that. You see what's happening. So it gets hot. That hot water, eventually behind it, would go through a condenser and cool down. Like how your refrigerator works. Right? Or your fridge freezer. We need a sort of around the back. There'll be a separate thing here, so with a condenser column in it, like that. Sort of radiation on it. Well, radiator blades on it. And then, of course, that. You see how that is. So, lasers in there, something like that, and then you smash all your particles in there. There you go. That's my theory on it. And of course, all of the inside of that will be rotating, or at least, yeah, either the container would be, or that guy would be solid, and the rest of it would be rotating. So everything there will be concentrated into a point. There is something in the universe that also does that. I'm going to quickly show you 1 minute. Now in the universe, this sort of does happen, and it's known about. I don't really think we need to look at this now. Silly drawing, but we're just going to have a look at quickly the whole principle of it. Alright, so what we need is an accretion disk. Yeah, good enough. A singularity. And a beam. X-rays. We'd also have gamma out of that. And sort of alpha out of that as well. Does look familiar, that, doesn't it? Yeah, pretty much black holes, pulsars, quasars, blazars. Similar sort of thing. Similar to our wacky drawing, basically put. I guess now we just have to find some way of building it. Yeah, right. Yeah, right. Not sure how we're going to do that. They want this uranium powered. That might be a bit difficult. Yeah, getting hold of uranium. No, that's not going to be possible, is it? Really? That would mean that I fall under the whole nuclear proliferation treaty. Yeah, civilians are not allowed that stuff. And would you let me anywhere near uranium-235 or 238? Probably not. If my destruction and destructive capabilities towards microwave ovens are anything to go by, you probably wouldn't want me unchecked and anywhere near that stuff. No. But anyhow, that's not the reason why you called. Oh, I've not even had a beer yet. 1 minute. Right, and that brings me to the final conclusion of this, actually. I'm not sure if I just did cover it. I've covered a lot on this so far. Yeah, I think I did sort of touch upon it earlier on, which is why NASA wanted to be using fission reactions in the first place, because of the whole nuclear proliferation thing. Right? Not only that, but yeah, I'm going to show you something very interesting, which you really, really don't want happening. And it goes something like this, actually, which is probably the main reason. Right. Come back to our little whiteboard quickly. And this would be really bad. Another pen, do we? Yeah. Green, blue, and red. That'll do perfectly. Green. Right, so we have our little rocket thing here. Right, and they decide that if this was nuclear based, they were going to go. Right, so they launched the damn thing up. Right, and something kind of goes wrong. Right, so now they're up here. This thing is doing what it's doing. And then, all of a sudden, that happens. And bits of that start falling over a massive area. They really don't want that happening. So, fusion ain't going to be happening, because that's another way for basically you're strapping an atomic weapon, for want of a better word of it, to a rocket and firing it at the moon. Right. I can't imagine the International Atomic Agency, or certainly any international treaties, agreeing to that for a minute. And bearing in mind there is the whole Space Nuclear Proliferation Treaty. So, yeah, fusion, I'm afraid, is out. Fission is questionable. Cold fission, the idea I proposed, touchy area. Right. Even with that, you're still potentially running the risk of a powder on there, unless it was going to be liquid based. And then when you subject that liquid to the vacuum of space, draws all the liquid out, leaving just the powder. That could be possible. Or failing that, then you essentially have to use the whole solid core. Again, with the dirty diamond, it could be done, so instead of having it sort of ferromagnetic, you would have the diamond essentially made out of the uranium. So it would be a composite of the two then. And you would rotate that really quickly. I would need to work out the design parameters for that. Nonetheless though, this isn't going to be easy. And bearing in mind submissions are due sort of in February with that. That's not really leaving a lot of time, but then again, I don't really want to be ploughing a lot of effort into this because it's probably not going to happen. It was just a sort of fun thought experiment. But who knows? I guess you don't know unless you try, do you? I'm sure the idea is a little bit complicated than many, but more simpler than others. But I reckon that's the way to go. But anywho, I thought I'd share that one with you. Links are in the description bar below. Give it a read. If you think that you have other ideas to it, give it a go. And there it is. They want to put a nuclear power plant on the moon by 2030. Well, the interesting thing is, if I got a contract for it, I could certainly potentially put a kind of working prototype together way before that. That's 8 years. That's a long time. And I've obviously already done a lot of thinking on it. It's how feasible it is. But it doesn't really violate any laws of physics, does it? Right, we're not on about perpetual energy here. But there are a few sacrifices that need to be made. They didn't want solar panels on it. You might have no other option. Right. And certainly the fuel, well, you've got whacking great moon dust there, which is probably heavily irradiated. Cosmic rays and certainly, well, yeah, out of space. Certainly going to be irradiated, so we can use that then. And what's interesting about my theory, look what they have there. A mining rover. Forward thinking. Let me know what you think to this in the low bar, anywho. And even if nothing, at least I've drawn a funny food blender. I wonder what we could make out of that. Doesn't look an awful lot out of place for a centrifuge. Interesting that, isn't it? Anywho, right, I'm out of here. I need to finish this. And I need to turn in. I'm done for the evening. Stay creative and explore. Right, and to the heavens. I'll keep you updated on how this one goes. Till the next time. See ya.